Hello everyone, I'm Professor Harrison and welcome back to our module on probability for finance. Today we're going to be covering the Bernoulli distribution and the binomial distribution. These are two of the most important discrete distributions in all of statistics. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's working through what happens when you take a simple binary outcome and repeat it over and over, and what the math says about how those results pile up. He opens up another one of those mysterious letters. Think about the simplest possible random experiment, one where the outcome is binary. It either happens or it doesn't. No middle ground, no third option. Think about a corporate bond. Over the next year, that bond either defaults or it doesn't. Here we have one trial, but two possible outcomes. A Bernoulli trial is exactly like that. It is a single experiment with exactly two outcomes. One outcome gets called a success and is labeled 1, and the other is called a failure and is labeled 0. The defining property is this. The probability of success is some fixed value p, and the probability of failure is 1 minus p. That's the entire setup. The Bernoulli distribution is the probability mass function built on top of that trial. It assigns probability p to the outcome 1 and a probability 1 minus p to the outcome 0. Written compactly, the probability of outcome x equals p raised to the x times 1 minus p raised to the 1 minus x. Let's think about why this works. If we plug in x equals 1, then we get p, and if we plug in x equals 0, then we get 1 minus p. So our probability mass function just converts the outcomes to the probabilities of those outcomes. The expected value follows directly from the probability mass function. The weighted average over the outcomes is 1 times p plus 0 times 1 minus p, which ends up just being p. The expected value of a Bernoulli random variable is its own success probability. That should feel right. If you ran this trial a very large number of times and averaged the results, the average would converge to the probability of a success. The variance is p times 1 minus p. This is worth slowing down on. When p is close to 0 or close to 1, the variance is small. That makes sense. If success is very unlikely, you already know what is probably going to happen on any given trial, so there's not much uncertainty. But when the probability is 1/2, the variance hits its maximum value of 0.25. The most uncertain Bernoulli trial is the one where both outcomes are equally likely. Now extend the setup. Instead of a single bond, you are holding a portfolio of 10 corporate bonds. Each bond independently defaults over the next year with a probability of 4%. Now we are no longer asking about any single bond. Instead, we're asking about the total count of defaults across all 10. So how many bonds end up defaulting? That count is a binomial random variable. So how do we model this circumstance? Well, before we write out the formula, there is a counting problem that needs solving first. Suppose exactly 2 out of the 10 bonds end up defaulting. Those 2 defaults could fall on bonds 1 and 2, or bonds 1 and 3, or 2 and 7, or any combination of the 2 different bonds within the 10 out of the portfolio. So the probability has to account for all of these possibilities. The number of ways to choose exactly k items from a group of n is called a combination, written C of n and k. If you've taken a statistics course, you may recognize this formula. The formula is n factorial divided by k factorial times n minus k factorial. What we are doing is counting how many distinct groups of size k we can form from a total of n. For 2 defaults from 10 bonds, that is C of 10 and 2. So if we wanted to figure out how many different ways 10 bonds can end up defaulting 2 times, then we would take 10 factorial divided by 2 factorial times 8 factorial, which works out to 45. So there are 45 distinct pairs of bonds that could end up being the defaulting 2 in the case that 2 out of 10 bonds end up defaulting. Now, the binomial probability mass function has 2 pieces. The first piece is that combination count, the number of ways exactly k successes can be arranged across n trials. The second piece is the probability that any one of those specific arrangements ends up occurring. That is p raised to the k times 1 minus p raised to the n minus k. Multiply those together, and you get the probability of exactly k successes in n independent trials. Let's work through the bond portfolio. In this example, we have 10 bonds, and the probability that one individual bond defaults is p equals 0.04. Let's start with 0 defaults. C of 10 and 0 is 1. There's only one way that we can end up getting zero defaults, which is that every single bond survives. Now, what's the probability that this occurs? Well, we would need all 10 bonds to survive, each of which has a 0.96 chance of occurring. So we take our 0.96 and raise it to the 10th, which would be the circumstance that all 10 end up surviving. This ends up coming out to around 66.5%, or more than 2/3 of the time, a portfolio like this will end up with no defaults at all. Now let's calculate one default. C of 10 and 1 is 10. This means that there are 10 ways for one bond to be the one that defaults. Then we need to multiply that by the probability of this occurring. If one bond defaulted, that means that it ended up in the 0.04 chance that a bond defaulted. The rest will end up in the 0.96 chance that they didn't default. So we take our 0.04, multiply by 0.96 and raise that to the ninth, and when we multiply it all together, we get about 27.7%. So the probability of two or more defaults is everything left over. 1 minus 66.5% plus 27.7%, which works out to about 5.8%. So there is a roughly 6% chance that at least two bonds end up defaulting in a given year. So the binomial distribution basically just asks two questions. The first is how many different ways can this outcome end up happening? Then the second is what is the probability of each of those different ways occurring? By multiplying those together, we end up getting the probability mass function of the binomial distribution. The expected value of a binomial distribution is the number of observations times the probability of success. So for example, if we have 10 bonds and a 4% default rate per bond, then the expected number of defaults is 0.04 times 10, or 0.4. So on average, less than half a bond will end up defaulting, which makes sense. 4% default rate across 10 bonds is almost never going to give you more than one or two defaults in a given year. The variance of a binomial distribution is n times p times 1 minus p. So in our example, that is 10 times 0.04 times 0.96, which gives us 0.384. Notice this is exactly the Bernoulli variance scaled up by n. This isn't a coincidence. The binomial is the sum of n independent Bernoulli trials. Because they are independent, the variances just add up. You end up with n times the variance of a single trial. One more quick thing about the shape of this distribution. When the probability is small, like 4%, the distribution is going to be right skewed. Most of the probability piles up at 0 and 1, and there is a long thin tail extending out to the right. When the probability of success is close to 1, then this shape is going to flip and the skew goes left. When the probability is close to 1/2, the distribution is roughly symmetric and starts to look a little bit more bell-shaped. We are going to see that symmetry again when we go to inference. Danny puts down the letter. He's been living the binomial distribution his whole adult life without knowing that it had a name. He thinks about a roulette session he had from a few years back. A night at a casino where he sat at the wheel and just kept betting on red. The same bet, the same wheel, spin after spin. A standard American roulette wheel has 38 slots. 18 of them are red, 18 of them are black, and 2 of them are green. The idea behind roulette is that you can bet on red or bet on black, and if you end up being correct, then you can double whatever your bet was. The green is the house's way of taking its own share of the profits when no one gets paid out if things land on green. So every time Danny ended up betting on red, the probability he would win and double his money on a single spin would be 18 out of 38 possibilities. So it's just below 1/2, 18 out of 38. That single spin is a Bernoulli trial, but a full session of 20 spins is a binomial random variable with n equals 20 and p equals 18 over 38. The expected number of wins is 20 times 18 over 38. That works out to just under 9.5. If all of his bets were the same, then he would need approximately 10 bets to break even. That gap is roughly half a win over 20 spins. That is where the house edge lives. Each session, he's expected to come up about a half of a win short. Not because of bad luck, but because of the arithmetic. In a sense, the 2 green slots are the house's edge built directly into the probability mass function of the roulette wheel. So that covers the Bernoulli and binomial distributions. The Bernoulli distribution is the foundational piece of the binomial distribution, where a single binary trial with success probability p has an expected value p and variance p times 1 minus p. The binomial counts the total successes across n independent Bernoulli trials. Its probability mass function has 2 pieces: the combination count for how many distinct ways k successes can be arranged, and the probability of any one of those arrangements occurring. The expected value of this is n times p, and the variance is n times p times 1 minus p. That is the Bernoulli variance scaled up by n. These end up being some of the most frequently used building blocks in statistics, and you are going to see the binomial again when we get started with proportions and count data in inference.